Hello everyone, welcome to the first video lecture of EC5201 Embedded System. In the first unit, we have learned about embedded system, general purpose processor, digital processor, and then we have also learned about memory and its interfacing with the processor. In the second unit, we have learned about the interfacing of I/O devices with the embedded system, the various protocols which comes with it, and then we have also learned about protocols like DMA, USB, IRDA, etc. Now in this third unit, we'll learn about the design of embedded system, and then subsequently we will also learn about FPGA, and then we'll talk about the serial parallel network communication network. Now today we'll start with the embedded system design process. So whenever we would like to design any system, the first and the foremost thing which we submit to the vendor or to the company or to any person who is going to make our system is a requirement. So the first and the foremost thing which we need is the requirement. So what comes under these requirements? Some of the points which come under this requirement can be performance, now speed is considered as one of the most important performance, which also affects its cost, but it is not the only factor which decide the performance of the system. Other performance, we need to see the cost. Now the cost consists of two parts. The first part is the manufacturing cost. And the second one is the non-recurring cost or non-recurring engineering NRE cost. The manufacturing cost will consist the cost of the component and the cost of the assembly. So every single time we manufacture any design, it's going to be included. But the non-recurring engineering costs include the personnel and the cost of the designing system. So this type of cost will not repeat for every design. Now after the cost, we also need the physical size and weight. Now this physical size and weight, it may vary from system to system, but for the particular application it should be within a certain limit. And another important factor is the power consumption. Now if we are designing any mobile system, the power consumption needs to be very low. because it will depend on the battery. So these are some of the requirements for any system. One more thing which we need to remember when designing any system is that we cannot always have a very fast system and a very low power consuming system. Now between these two parameter, there is always a trade-off. If we have very fast system, the power consumption increases. And if we want any low power consuming device, then the speed or the performance decrease. So we have to mediate in between these two parameters. Now after having the requirement, the next thing which we need is the specification. Now this specification is going to be the bridge between the customer and the architect. Now the architect we'll learn about it in just after a few moments. Now whenever we give any specification, it should be clear enough so that someone can verify it to see whether the requirement and the overall expectation of the customer are being met or not. It basically is this specification tells what the system does. Now after the specification, the next thing is the architecture. Now the architecture describes how the system implement the function of the system. Now after architecture, what we have is the components. Now component can be both hardware as well as the software part. Now in hardware we can have FPGA, we can also have boards, and then we can have microcontroller, etc. And to run the hardware we need some software. Now the final thing after having the component is the system integration. The system integration is the final process. Now what is system integration? The name itself implies that it is integration of all the components which we have designed in the upper process. Now while doing all of this, we need to debug at every stages. Now if we debug at only a certain stages, then we may uncover some simple bugs. Bugs means the error in simple or the layman language, and we may be able to fix it. But once all the system has been integrated and within simulation or anything, then if the system is quite large, then debugging may be a challenge. So this is the design process, a very basic design process. So this is what we call a basic design process. So once we have this basic design process, we can see the various challenges while designing any embedded system. So next is challenges. Challenges in embedded system design. So some of the challenges are environment, adaptability, power consumption is, if mentioned before, area of the device, packaging and integration, providing security is also a major challenges. So these are some of the challenges. These are not exclusive. We have left many other, but these are some of the challenges while we design any system. So this is a basic. Now let's say we have a system and we would like to design the system, or we would like to try it. So how can we achieve that? One way is to design it through the use of microcontroller, and another way is to design it by using FPGA. And so what is FPGA? Microcontroller we have learned in the previous classes. So today we'll talk about this FPGA. So FPGA stands for Field Programmable Gate Array. Field Programmable Gate Array. It's an IC. It is basically an IC which consists of a multitude of blocks, very small blocks, which we call as CLB. Now if we have since we have microcontroller, why don't we use microcontroller to design any system? The first and the foremost reason for not using microcontroller for designing any system is that once the program has been burned in a microcontroller, the program cannot be changed in the field. It doesn't mean that it cannot be reprogrammed. And another reason is that the speed of execution is much faster in FPGA. So FPGA is basically used to design a system, basically used for prototyping. In simple language, we can say that it is used for prototyping, and the speed while for the execution in FPGA is much fast. We cannot say that it's faster, but it's very fast. So nowadays we generally use FPGA to prototype. So once the prototype is passed, we can design specific controller or IC for the device. So that's basically called as ASIC. So what is we'll talk more about this FPGA. So as mentioned before, FPGA stands for Field Programmable Gate Array. Is basically an array of logic gates. It's basically, in simple term, we can say that it's an array of logic gates, not exactly logic gates, but it's an array of blocks which are called as CLB. So if we look into it, it will look something like this. Inside any FPGA, there will be a multitude of micro blocks. These blocks are called as CLB, configurable logic blocks. A CLB can be considered as a micro circuit or digital sub-circuits which can implement various type of functions, not only logic gates. These CLBs are interconnected through the use of buses. There will be multiple buses, and we'll draw three type of buses: control bus, address bus, data bus. So there will be multiple buses which will run around the CLBs. So it will look something like this. All these CLBs are going to be connected by using these buses. Now we can connect these CLBs through the use of buses for various purposes. Now what are the advantages of using this FPGA? Now the design process or the verification process in FPGA is very less. So basically it requires very less time, starting from design process to functional chip or design. Another advantage is no physical manufacturing is needed. The only disadvantage is that its cost is high in comparison to microcontroller. But once we have an FPGA, we can use it repeatedly. So if we buy an FPGA for prototyping only a single system, then the cost will obviously be high. But if we are going to prototype multiple devices, then buying FPGA is a smart choice. So the next part of the lecture is how do we program an FPGA. Programming FPGA. FPGA is programmed by using HDL. HDL stands for hardware description language. Two most popular hardware description languages are Verilog and VHDL. We can use any of these two languages to write program for FPGA. Though there are some similarity between these two programming languages, they are fundamentally different. So what are the design flow in FPGA? Or the programming in first and foremost is design of project. The first and the foremost thing is design of project. Now we have to write code either in VHDL or Verilog. So once we have the design, we have the code, we are going to do synthesis. After synthesis, we are going to run simulation. After simulation, we are going to translate the output. Now, while simulation, if there is any error, we have to go back and then we have to rewrite the code again, and then we have to do the synthesis, then simulation. Now, if there is no error, we can translate. Now synthesis takes the language or the code and then translate into the netlist, which is shown as a circuit diagram or schematic. The synthesis, after the synthesis, we go to the simulation. In the simulation is used to verify the design specific in the netlist whether it is correct or not. Once the design is verified, we can convert the code into binary format. Now after this, after the translate, I'll need to write it in the new page. After the translate, it's mapping is done, then place and route, and then finally on chip design verification and debugging. Now the best thing about using the software is that all of this process all this process will be done by the simulator itself. like Vivado, all of this step, what we need to do is we need to write a code. Basically we need to write a code, and all of these subsequent steps are going to be done by the simulator itself. So it basically simplifies our process. So this is a design flow in FPGA. So the first thing, we have to write a code, and after that we are going to synthesize it. While synthesizing, it's going to translate the code into netlist, which is a description of the circuit diagram, a textual description of the circuit diagram or the schematic. Now once we have done the synthesis, we are going to simulate it to verify whether there is any design error or the specification has been met or not. Now after this, we are going to convert the code into binary format. So once you have the binary format code, we can burn it into the FPGA. So this is some of the basic, this is the design flow in an FPGA. So in the next part of the video, we'll talk about Verilog. It's an HDL language. So for now, we'll wind up here.